For today's topic, we are going to discuss um, Zcash again. And in particular, we're going to talk about unified addresses and Orchard transactions. So you probably know that NU5, the upgrade for Orchard was a few months ago, and it opened the possibility of having unified addresses. So far, most of the wallets have been under using UA, meaning that they are supporting UA, but in a somewhat limited fashion. And today we're going to talk about how we can, what they offer, how they work, and what they offer, and why it makes making private transactions harder than it used to be, if you want to use them to their most high potential. So there's not going to be much coding. It's going to be just in Python. But I think it's going to demonstrate well the difficulties and the challenges with our Orchard transactions and the unified addresses. So as a recap, you have in Zcash three different pools. We have transparent addresses. Let's say this column is T. It would be for transparent. S would be for sapling, and O would be for orchard. So an account, a wallet, can have funds in three different kinds of pools. It's as if you have a bank account, and inside your bank account you have usually sub-accounts, like for checking, for investment, and for savings, for example. So three places where you can hold coins, money. And in the past, the user would know exactly which pool he would be using because they would have different addresses. And the addresses in T, starting with T, would be for transparent. Something that starts with ZS would be a sapling. But now with Orchard, we don't have actually legacy addresses. We don't have addresses that are uniquely for Orchard. We don't have ZO addresses. So the legacy addresses would be only the T addresses and the ZS addresses. Everything else would be UA, U1 actually, unified addresses. But the trick with unified addresses is that you can have more than one address inside the UA. So a UA is a container actually for addresses, for account numbers if you prefer. And you could have only one account number inside. You could only have the location or the address of your Orchard account. You could only have the sapling or the sapling, but for some reason you cannot have just a transparent. So you can have sapling, Orchard, but you can also have two of them. You can have in a single UA, you can have transparent and sapling receivers that would allow sender, somebody who sends you coins, to select either your transparent address or your sapling address, knowing that you are able to receive the funds in both locations. They would end up in your global account the same way. Some would end up in your checking account, and some would end up in your saving accounts. A modern wallet should be able to manage these two endpoints or two addresses or receivers smoothly and allow you to interchange fairly easily. That is not yet completely the case. So most of the wallets still make the distinction between transparent and sapling. But moving forward, we hope that this handling will be taken care by wallets more than by users. So here I have in this sample case, I have the 7 different kinds of orders or addresses. So let's say that, for example, I want to make a payment to 7 different people, and they have given me 7 different kinds of addresses. So each of the kind that is possible. So if you 1 to 7 here, I just put it as let's make it big screen. And let's make it just a regular automatic number. Right. So the first one wants to receive 0.1 ZEC, and he gives me a transparent address. The second person gives me has a sapling address, a ZS, and he wants or they want 0.2 ZEC. The third one gives me a UA, and they want to receive 0.3 ZECs. And now it becomes a bit more funky because the fourth one actually gives me a transparent plus sapling address. So a UA that can receive both transparent and sapling funds. So actually these guys here should use color to indicate the receivers that they can take. Let's put that in like blue. So we have, oh, not this guy. Set the this one reset and this one blue, right? So I will mark in blue in this color the possible places where these guys can receive funds. So you can receive funds here. This one is going to be a transparent and orchard, sapling or orchard, and this one is all of them. All right, so I indicated one color, this color. All right, so the first one was transparent, separated saplings. Third one was UA orchard. The fourth one is a UA transparent plus sapling. So here, even though I said it's 0.4, technically you can have any split of funds as long as the total is 0.4. Then we have a transparent and plus orchard for 0.5, a sapling plus orchard, and finally a UA that combines every kind of receiver. So this is going to be actually moving forward. Hopefully, the most common kind of UA, basically UA that can receive any kind of funds, whether it's transparent, sapling, or orchard. And this guy wants 0.7. All right, so these are the basically the transaction I want to build, and all these are the outputs that I would want to have, I need to have. And here are some for each pool, the quantity that has to go out. Only so once we make the decision, so this one is a transaction I do manually. So assuming that supposing that I'm going to do this allocation myself, or I have a wallet that basically automatically chooses the highest pool, which in this case, when there is a transparent and sapling, it would choose to send all the funds in the highest possible pool, which is sapling. So in other words, the receiver is capable of receiving transparent or sapling, so I will send sapling. Here it can receive transparent or orchard, therefore I send orchard. And same applies to the rest. So all the transaction would be made using sending funds in the highest privacy pool or the most recent pool. So this gives me this allocation of funds, outgoing funds. And then I can sum the per type. So I would have 0.1 in transparent, 0.6 in sapling, and most of the funds will go to the orchard pool, so 2.1 in orchard. And the total of these guys here must be the total of this guy here. So I can check that this total here is 2.8, and I have really 2.8 as well here. Now, the way I selected the funds, I want to minimize the information leakage. So when you make a transaction, any transaction on Zcash, what you expose to the blockchain are anything that is transparent. So this value here will be, of course, seen, known, as long as the address. But if I pay somebody with using my own transparent funds, I will also show the amount that I have used. So this value here would be shown. But when it comes to the shielded pool, the values are here are not directly seen. what you see is the difference between the inputs and the outputs in as a amount, as a total amount. So if I send 0.6 out because I chose these receivers, and I take funds from my own sampling pool of the same value, 0.6. So here, basically, what I'm saying is that I have a wallet that has, for the sake of this case, I have a lot of funds in my own transparent sampling and orchard pools. So I can freely use my funds regardless of which pool. So to minimize information leakage, I would match the quantity that people receive so that the difference is 0. And I do that because the difference is what is going to be exposed on the blockchain. So by doing that, I actually expose 0 data here. People would not be able to know the amount of data that of funds that have been exchanged. And the same thing for the orchard pool. So also fund with 2.1. So the only information that has leaked or that is visible is the amount of funds that I have put in that I've taken from my transparent pool. And I ignore this one because regardless of my strategy, regardless of however I choose to allocate outgoing funds and incoming funds, inputs and outputs, this is going to be shown on the blockchain. This is a receiver transaction, transparent transaction. So this will always be seen, and I can therefore eliminate. It's nothing that I can improve on. So what I want to improve is to reduce this value. So this value, this value, this value, sorry, this value, this value, and this value, right? And since these values here can be negative, right? I could put more funds in than out. What I want to minimize is the square of the sum. So here I have a square of well, it should be, these are just the differences, and then my badness or the sum that I want to minimize. So the spread from the perfect hiding. Perfect hiding would be 0, and it's only reached if you have used no transparent funds to from your own wallet, and you have somehow matched the sampling pools exactly. So this guy will be 0, this guy will be 0, and this guy will be 0. In that case, and only that case, information disclosure would be 0. So that value here is basically the square of this plus the square of this plus the square of this. This guy is just equal to that guy, right? So that guy here is equal to this one. The format is as automatic. This one is the same as this one. This one is the same as difference of this one, and this one is the different as this one. What we do here is we square this, we add the square of this, and we add the square of this. So this is our the value that we want to minimize. And you can see that if I do the most natural, the easiest way to allocate funds, and this is the case if we have unlimited funds in the transparent sampling and orchard, and we choose to use orchard or sampling when we cannot use the orchard, then we have the like error, we have a badness of the 0.01. Right? So let's go and see how we can improve on that. And we can see that improving on that is not going to be easy. It's not going to give solutions that are intuitive. So the first one I want to show is if instead of forcing the highest pool, we want to choose anything possible here. So we are okay with using any of the blue squares, blue cells, as long as the sum here is 0.4, the sum here is 0.5, the sum here is 0.6, and the sum here is 0.7. And we also are going to make sure that the inputs that we take, so these guys here have to match this guy here, right? So inputs have to match 2.8 as well. Then we calculate the error as being what we take in sapling minus what we use in sapling, so the sum of this column. So this guy here is the sum of this. This guy here is the sum of that. And this guy here is the sum of this. So these three columns. These guys here are the inputs that we take from our wallet. So it has to sum to 2.8 because there's no fee in this transaction. And finally, then we can calculate this badness coefficient. So let's optimize that and see that with the optimizer, we can lower this badness value to 1/3, to much lower than it was. It is now 1. Before it was 0.01, and now we have 1/3 of that. And when we reach this, what happened is that intuitively, we start splitting the nodes here. We are not using only one pool for the transactions that offer using several pools, right? So here, we could have used this one, we can use sapling or orchard, and this one can use transparent, sapling, and orchard. So the algorithm will avoid using transparent. We can see that it has automatically avoided using transparent because we pay a hefty price in using transparent. Every node that is being transparent, that is shown here, will be added here and cannot be offset by anything because in our minimization formula, we are basically saying that this not a net change, it's the absolute value here that is going to be squared. So the solver has figured out by itself, thanks to like I don't know AI whatever, right? That using transparent is not optimal. So instead, it has decided to use sapling and orchard, and you can see that the distribution here, the allocation, is not something that I would personally have found by myself. It still sums to 0.6, it still sums to 0.7, but by using sapling here, instead of only using orchard, we can see that the spread here between the input and output is well, it's not 0, right? Before it was 0, so it was perfect. But we have something that is still close to 0, and we have taken away from, we're not disclosing as much in the transparent side, right? Because before, we had this 0, 1 transparent to match this one here. Right? So there are so many things to make sure, right? So if you only put stuff here, you still have to pay for this one here. So you have to bring something in to amount for this transparent output, and the result is this, right? The result is 0.003. The problem here is that we have reduced the amount of transparent funds in our transaction, right? So we have 0.03 instead of 0.1, but we still have some, right? So we still have we're still using some transparent funds. If we also ask the solver to not use any transparent funds from our wallet, right? So we don't want to have any of that here. Obviously, we're going to have some here, and we may have some stuff here. This guy is allowed, right? So we have let's put the colors back. So we could have this, and this, right? So these are the crap. This, this. So these are all the cells are possible. These are false. So in theory, we could have outputs here. We let the solver decide whether it's better or not. But we surely don't want to have inputs, transparent inputs. All right. So if we add this condition, now we have another solution, we have another distribution, where here you can see that there is no transparent inputs from our side, and the solver was still able and still find it optimal to not use any transparent funds outside as well. So the only transparent fund is amount is on the receiver or the first recipient, and we cannot do anything about that because he has only given us a transparent address. But for anybody else, even though they're okay with receiving, so this guy was okay with receiving transparent fund, this one too, and this one too. The solver has figured out that that's not a good thing to do if we want to minimize information leakage. And you can see that the information leakage here is 0.005, which is worse than if we the case before because we have added one constraint, but it's still twice as much as what we had if we're doing it manually. So now we have 0.005. And so the result though is that we have a slightly different allocation here. And other than that, we also see that because the formula is symmetrical in sapling and orchard, it seems like the solver has also ended up with exactly the same net difference in sapling and orchard. So also it's a bonus that you don't really know if by seeing this transaction, since it's symmetrical in sapling and orchard, you really don't know much about which pool was privileged from the point of view of this transaction. So no transparent funds were used besides well, from our side, and we have a net change of 0.05 ZEC. So what if we continue with more and more constraint by saying that so far we have said our wallet has unlimited funds. It can choose any allocation it wants. Here it has shown that we need 2.8 ZECs to execute the transaction, and it has taken 1.37 on sapling and 1.43 in orchard. But what if we say that we don't have 1.37 ZEC in sapling, and our wallet has only 1 ZEC in sapling pool? So we add another condition here, saying that we still don't want the transparent addresses, the transparent pool, sorry, but we also want to have this value lower than 1 because that's the funds we have. So in this case, the solver will allocate the transaction differently and decides that it can do pretty much exactly the same, very close, same badness result, but now with only 0.93 sapling. And of course, it has to use more on the orchard pool, right? So the spread here is actually still the same, but it just has put more on this side. And then if you have the opposite case where you have more orchard, you have more sapling than orchard, and you want to limit the orchard usage to 1, you can also switch the constraint to be a constraint on orchard usage less than 1, and now you will have something like you will have this result, which balances back the usage to the sapling pool. So you can see that these guys and these guys are very similar, except that obviously here we have to use more. We have to use less sapling than here because we are limited to 1, and here it's the opposite. Right. All right. So the solver, this solver is very pretty flexible, and you can see the code. It's the code in Python at the moment, and it's basically a problem of quadratic minimization with constraints. So, well, I'm using just a few matrices. So these equations here, basically, and these matrices here, they are implementing this particular problem. And once we have exposed this problem like that, by defining PQ, so PQ form the parameters of the function that we want to minimize. So PQ represents in linear algebra form this equation, and as an equation of under x. So the unknown are this one, this value here. Okay, so actually it's pretty easy. It's all the blue values plus these values here. So these guys also are unknown. So all these blue values here are the variable to our problem. And there are 12 of them. 1, 2, 3, we have 12 of them. So the solver will find these values. And all the other stuff here, the constraints here, are expressed in this matrix here, plus these constraints here. So for example, when I say that t equals 0, t equals 0, meaning that guy here was 0, I just said by saying x of 3 equals 0, right? And the solver takes care of that. So it's deceptively simple, but the algorithm, the solver, is actually very hard. And so far, it's still in Python. So one of the work is to embed this solver in the wallet. All right, but until then, I still wanted to show that the problem is still far from being trivial, and without I think without a solver, we can't have really optimal solution. We could go for this one. I think this one is what Zcash is using actually. But I would say that in terms of privacy, as a user, I would prefer to have something more flexible, which allows me to minimize this coefficient, this value here that it represents the information leakage. And also, you can change the formula here. It's here it equally weights sapling, transparent sapling, and orchard pools. So, for example, if you want to say that you really don't want to have, you want to you want to penalize the transparent pool by saying that any value that is used in the transparent pool, like B13, anything that you will use, instead of just squaring it, you can also multiply it by a value, by a weighting value. And the same for sapling. If you want to say that, okay, this net change here, you want to penalize more than if it's a orchard change, then you could also put a constant weight here. Say, for example, that it's not square, but it's 10 times the square. 10 times the square. So obviously, if you do that, you have to change the solver. You have to change this stuff here, right? Some of the values here will change, but the form of the problem remains the same. So I would say that this approach is quite flexible because you can decide on a lot of configuration based on your own preferences. All right, so that's what I have to say for today. Hope you like it, and I'll see you around.